This video looks at the process of how to derive an expression for the covariant derivative from first principles that involves changes in basis vectors on some manifold. It shows how the end result is not a tensor, but rather a tensor-like object whose rank is increased by one higher than the tensor it began with. So, given some vector field v of x over some part or all of a manifold, we can find its derivative with respect to the coordinates x that label the points in the manifold. So we've got some vector field over a manifold. Now first we write the vector in terms of its contravariant components and its covariant basis vectors. So contravariant components here and covariant basis vectors here. Now the derivative of this vector is the partial derivative of this object here, which is the partial derivative of the components times the basis vectors plus the components times the partial derivative of the basis vectors. So that's the derivative. Now the last term on the right is the derivative of the basis vectors and plays a significant role in curved geometries. In flat space this will disappear, but in curved geometries this doesn't disappear. So on a curved manifold in a curved space, that partial derivative there is not zero. Alright, now in flat space the basis vectors are the same everywhere, from point to point. In the x direction, in the y direction, in this two-dimensional manifold here, this case here, two-dimensional Euclidean space, these are constant unit vectors and their partial derivative is zero. They're constant, wherever you look. Now, so the derivative of a vector in flat space is dv dx beta is the partial derivative of the components times the basis vector. That extra term we saw on the previous page disappears here because these are all constant and their derivatives are zero. In curved space though, the basis vectors vary from point to point. So at point A, here's E1, at point B, here it is again, at point C, here it is again. Now these basis vectors are tangential to the coordinate curves. These coordinate curves mark out these orange and blue lines here. These are the coordinate curves for this surface, which is a manifold. And these basis vectors are the partial derivative of the position vector in Euclidean space, and that gives you these tangential. They are tangential to the coordinate curves. But from point to point, you can see they're not constant. They differ from point to point. Same basis vector, but different point on the manifold. So that means the derivative of the vector involves both a change in its components as well as a change in its basis vector. So we end up with the partial derivative of the vector is this object here. So that's the derivative of the vector. Alright, now for a covariant basis vector, that's one with a lower index, then this partial derivative is equal to this object here, this Christoffel symbol of the second kind, and then expand it out in terms of basis vectors. Notice the gamma here means that we sum across these for whatever dimensions we're in. For the contravariant basis vector, that's for the upper index here, then we get this object here, and we notice that the alpha here matches the alpha on top of the gamma here, mu beta, and expanded in the contravariant basis E mu. And we sum across this lower and upper mu here. The Einstein summation convention applies here for whatever dimensions we're in. So we can write now that dv dx beta, now this is for the contravariant components and covariant basis, this partial derivative. Now, the partial derivative of the basis vector dE alpha dx beta that we saw on the previous page becomes this object here times that. Okay, and then what you're going to see, and will be important, is that notice this basis vector here, the index is gamma, and this one is alpha. Well, we can rename indices, and so this gamma here and here can swap place with this alpha and alpha here. They can swap places because it doesn't matter what we name the indices. We're still summing over the same number of dimensions. So we swap those, that gamma and the gamma and the alpha swap, the gamma and the alpha swap, and we get over here E alpha here and E alpha here, which you'll see later on we will factorize out, and we'll be left with an expression for the components. Anyway, more of that'll come later. Alright, so to see what this means, what does this change in the basis vectors mean, and how does it affect the derivative? Let's start with a manifold like the one below, and here we have a point P, x mu, coordinates, point Q, x mu plus dx mu, so they're infinitesimally separated. small separation between the two on the manifold. We use this curved surface here because it's easy to demonstrate what we're about to talk about. Alright, so let's say there's some vector field on this manifold, and so at point P, the vector is here, points this way, and at point Q, the red one, it points here. So this is the vector at x mu plus dx mu, so infinitesimally separated by the amount dx mu in coordinates, but they are separate. They are two separate points on the manifold there, and so they have different basis vectors, and so it's not a simple matter of adding, subtracting vectors on manifolds anymore because they have different basis vectors. Very different to flat space where we add and subtract vectors all the time because they are the same basis vectors. Here they have different basis vectors. Alright, so next step, we now parallel transport the vector at Q here, keeping it parallel to itself. We follow the process of parallel transport across the manifold here to the point P, and we notice that for a curved surface or a curved space, a curved manifold, these two, when their points at the base of the vectors join up, there will be some gap here, and that represents the intrinsic curvature in the space. And we've seen that with the Riemann tensor. Alright, next bit. Now consider the difference between the vectors at the point P. So this was the red one is the one we parallel transported across to the original vector Vx mu, and here's the difference delta V. So delta V is Vx mu parallel, that's this one at point P, our original red one, we parallel transported over from x mu plus dx mu across to here. So delta V is Vx mu parallel minus Vx mu. So delta V is the difference between these two. They're now at the same point, P, and so we can compare them because they share the same basis vectors at this point. Alright, now the condition for parallel transport is that the derivative of the vector is 0. So from earlier, we saw a couple of slides back, this thing set to 0 means that this is equal to that, same basis vectors here, and that means that this component is equal to this part of the component. So, alright, and that gives us a help in deriving an expression for the covariant derivative. Now we can use this to determine the form of the vector components at the points P and Q. And so what we'll do is we're going to integrate this expression from x mu plus dx mu, that's the point at Q. We parallel transport it back to the point x mu, so we'll integrate in that order, this expression here, and the same on the other side as well. Okay, on the left here, given this is an infinitesimally small displacement here, then we have the vector at x mu and the vector at x mu minus dx mu. Now, only is this approximately true in the case that dx mu is small. So these are infinitesimally small difference between them. You can't normally add and subtract vectors on a manifold at different points. That operation doesn't apply. On the right here, for a small infinitesimal increment, this integral here is approximately equal to this, and maybe some higher order terms in dx beta, which we'll see will disappear off very quickly because they are infinitesimally small. So what we can say then is Vx mu, the vector at x mu, is approximately this vector plus this bit added on. Alright, so we have delta V is Vx mu parallel minus Vx mu, and we substitute this expression here like this. Alright, and so we can say this is approximately equal to this minus this plus that. Okay, now the covariant derivative is defined as you might expect by this del symbol V as being in the limit as dx mu approaches 0 of delta V, that's this object here, divided by dx mu. Or in component form, del or nabla subscript mu V alpha is the limit of dx mu approaches 0, delta V alpha and dx mu. Alright, so let's do that then. Alright, so we take this term here, if you remember from the previous slide, it's this object here, divide by dx mu. Okay, now notice here that this goes under here, and so we can separate that piece off. And the lim, as dx mu approaches 0 of this object, is a familiar derivative. It's the partial derivative, dv alpha dx mu, so it's the usual definition for the partial derivative there. And this object here, well, here the Kronecker delta applies, dx beta dx mu, and we have delta beta mu, And when we do that, that means that the beta here and the beta there become mu. So these somehow become mu, conical delta applies, and we end up down the bottom here with this expression here for the covariant derivative for the components of the covariant derivative. The components with respect to V alpha is this object here. In flat space, this gamma will go to 0, disappear, and we'll be left with just the usual partial derivative in flat Euclidean space, because these gammas are all 0. But in curved space, they are not. Next bit, now the object just produced is not a tensor due to the gamma term on the end there, and just have a look at tensors and tensor transformations to see how that is. So given the following coordinate transformation from the x coordinate system to the x prime coordinate system, the vector v of x is transformed into the prime system v prime of x prime. So the transformation law for a rank 1 0 tensor, that's rank 1 in the contravariant components, the upper index here, and 0 in the lower index. So it's a rank 1 tensor, which is what a vector is. This object then, if this is a tensor transformation law for a rank 1 0 contravariant tensor, this one here. Alright, now, same coordinate transformation now from x to x prime for a rank 2 tensor, that's a rank 1 1, or 1 in the contravariant index, 1 in the covariant index, 1 1. So the transformation law for a rank 2 or 1 1 tensor, in this particular case 1 upper 1 lower, is this particular object here. dx prime I, dxk, dxl, dx prime I, and notice here prime j, okay, over here gives us the prime here, dxi prime gives us this one here, and the k up here, the k down here, the l down there, the l up here, the I is on top because it's on top over here, and underneath the j is down here. That's the prime j. Alright, so 1 up, 1 down. Okay, next bit. Now, the affine connection is not a tensor because it does not transform as one. And to show that, if it were one, then you would expect that gamma CAB here would be multiplied by these terms here because there's 3 indices, so there should be 3 of these, and would be equal, then in the primed frame, it would be this. But we'll see that this is not the case. And so to begin, just remind ourselves that the partial derivative of the basis vector with respect to xb is this object here. Now, that implies that if we take the dot product of both sides with x contravariant c here, then the conical delta applies here, and this becomes 1. And we get gamma CAB is EC dot DE, partial derivative of EA with respect to xb. And so this expression here is what we will use to show that this does not transform as a tensor. Now, the affine connection has 3 indices, so we expect it to transform according to this, and we'll see that that's not what happens. Alright, so let's start from the beginning. Here we are. In the prime frame, we'd expect this. Okay, so let's just expand that out a little bit. Here's the first bit. Let's take partial derivative outside the bracket here and just leave the basis vector in the prime frame here. Now, next line down, this prime frame here can be expressed as this object here, because this will transform as a tensor according to the tensor transformation rule. This should transform like this, and this bit here should similarly transform like this. Okay, and the partial derivative out here. Next line down, we keep the first bit here, dot product, scalar product, and then over here, the partial derivative of this object, of the partial derivative here, gives us this double partial derivative here, times the basis vector EA, and then we have this term here, this part here, times the partial derivative of the basis vector, this object here. So we now separate this into 2 parts. Let's keep going. Okay, keep going, here we go, the first bit then, that bit here is not changed. Now if we go over here, we notice that before, on the previous page, we had this d partial derivative of the basis vector with subscript a with respect to dxb prime. Now that's in the x coordinate system, this was in the prime coordinate system, and I've probably should go back and show you that. See here, this is in the x coordinate system, this is in the prime coordinate system. They're two different things, so we can't have that. We can differentiate the coordinates with respect from x to x prime like that, but this object here is composed of xa's and so on. We can't directly differentiate it with respect to the primes. So next page over, what we then do is, this first bit here stays the same, expand that out, scalar product EC here, this object out front here, but here, this DEA, DXB, and we introduce this DXB here and this DXB here. And so these two operations here are allowed, but now we're differentiating the basis vector in the x system with respect to the x coordinates because it's a function of the x coordinates. So we're differentiating with respect to the x coordinates and not the x prime coordinates. So next line down gives us this object here. Here we are. Okay, now, so we have AB here, and this, we multiply this across here, so this dxc prime dxc is dxc prime dxc times these two here, there they are. Xc from here goes here, and this object, now this is looking a bit like a gamma term. So next line down, here we go. Kronecker delta applies here, so delta Ca, and over here, this becomes this gamma term here, gamma Cab. That is the definition of gamma Cab as we saw a couple slides back. Okay, so let's turn this around. Let's bring this term up to the front. So this second term here is up to the front down here in the final line. And this term over here, notice the Kronecker delta, the A and the A will sum out and become C. So, and they're replaced by the index C here. And so what we've got is that in the prime frame, gamma is this object, which is transforming like a tensor for the first part. But this second bit added on means that the gamma does not transform as a tensor. If it did transform a tensor, we'd only have the prime parts here for gamma is equal to this first term, but with this second term here added on, that means it does not transform as a tensor. So the gammas are not tensors. Alright, so the first part of this equation follows a tensor transformation law, but the second term does not. So here we go, this is how the gammas transform. Now the covariant derivative is made such that it produces an object that transforms as a tensor in that it forms a tensor field in the same way that a vector is part of a vector field. So the final object we end up with after covariant differentiation, taken as a whole, when you evaluate it, it produces a tensor object which transforms as a tensor object, even though it contains the gamma things here which do not transform as tensors. And so the covariant derivative, the end result, is not actually a tensor, but it is part of a tensor field, and each term when you evaluate them you'll just end up with a tensor which transforms as a tensor. So we say that it transforms as a tensor and then it forms a tensor field in the same way that a vector is part of a vector field. I know that sounds a little bit strange and so on, but the final object, if you just evaluate it and put in all the components and work them all out and so on like that, you'll get an object that's still a tensor and will transform as a tensor. Okay, so the covariant derivative of a type Mn tensor field is a type Mn plus 1 tensor field. So, and to see this, we must define the del or nabla operator, the covariant derivative operator, as this object here. Alright, or more compactly, the partial derivative can be expressed like this. Alright, well, del V gives us this object here, that, and V, the vector V, can be expressed in a contravariant component form like that, and covariant basis like that. And so E alpha tensor product is what this cross in a circle means, tensor product. Take partial derivative here, and we want the partial derivative of this object. We've done that before, earlier in this video. E alpha tensor product, this object here. Partial derivative of the components times the basis vector plus the components times the partial derivative of the basis vectors. On we go. Next line down, replace this with the gamma term and the basis vectors gamma. Now here, what we would like to factorize out is the E alpha and the E beta. So what we're going to do is swap those two betas with the two gammas, and then we'll be able to factorize out E beta as we've done on previous pages, previous slides. Gives us this object here. So the covariant derivative of the vector V is this object here. It has two indices. It's gone from rank 1, 0 to rank 1, 1, or it's gone from a rank 1 tensor to a rank 2 tensor. Rank 1 and and 0 is 1, 1 and 1 is 2, so you've increased the rank by 1. And how you've increased it is 1 in the covariant index, hence covariant derivative. Next bit, let's have a look at a vector. More generally, you should call this a one form. It has covariant components and contravariant basis vectors. These are, you'll hear them being called one forms. Alright, the covariant derivative of one form then is this object tensor product with this one, and when we do that, we get this. Same thing again, work this through. This time round, now this partial derivative of the contravariant basis vector with respect to the coordinates x alpha is equal to this object over here. Just a reminder, it's negative gamma alpha mu beta e mu. And when we put that in there, we get this. What we would like to factorize out is e alpha here and e beta. So we can do a little bit of swapping here. The mu's can become betas, beta, beta, and the betas here can become mu's. And when we do that, we get this object here, and then the tensor product of the two basis vectors. And that can be written as here. Again, we have two indices, so we've gone from a 0, 1 rank tensor, that's 1 in the covariant index, if you hear, W beta here, covariant index, the one form, to a rank 2 tensor, and that's 0 in the contravariant, 2 in the covariant. Next step, let's look at a tensor of rank 2, and we're going to express it this way. And here are the components, one up, one lower, so one contravariant, one covariant. We can have a tensor with both a covariant or both a contravariant. I just haven't got the room in this video to do that. So the covariant derivative of that is this object, tensor product of all this, EC, tensor product ddxc of all this object here. And again, same thing, let's work through that partial derivative of the components here, times this tensor product of the basis vectors. Then work through each one, so we have now the partial derivative of the basis vector and that tensor product, and then finally the partial derivative of the final basis vector and that tensor product. Okay, next line down, what we're going to have try and do now is replace these with the gamma terms. Alright, so this partial derivative of the covariant basis vector gives us a positive gamma term, and this partial derivative of the contravariant basis vector here gives us this negative gamma term here. Put those in. Over the page we go, and what we're looking to do is that EA, EB. We would like to factorize that out, because if you remember on the previous page, we did a little bit of swapping of indices here. See how we had the D here. That D and that D can be swapped with that A and that A, so we get EA here. And this D and this D can be swapped with this, we need to swap it with a B, so the B there and the B there. And when we do that, next page over, we've got EA, EB, EA, EB, EA there, EB. Factorise all that out, which was the point of swapping those indices. So it's this object here, this EC tensor product with all this, bring that over here. So here's our three basis vectors, the tensor product of those times these components. And then we can write the covariant derivative here for this rank 2 tensors being this object here. So we've gone from a rank 1, 1, that means one index, the A there contravariant, and the B there covariant, so 1, 1, to a 1, 2, which means that there is 1 contravariant, and 2, the C and the B covariant. Next one, so in general, for a tensor of this general mixed form, one upper indices and lower indices, the covariant derivative of that will just follow this format here, just a generalization of everything we've been doing. Each upper index gets a positive term here, each lower index gets a negative term, negative gamma here. Next bit. Now finally, covariant differentiation obeys the following two properties. It's linear, so the covariant derivative of the sum of two tensors is the covariant derivative of each of the tensors summed together, and then summed. Now the product rule or Leibniz rule applies, so the covariant derivative of the tensor product of two tensors is the covariant derivative of 1, and product with the tensor product with the other, and then so on and vice versa. And that's for two tensors A, B. And that's the end of that.